Hello friends, how are you? Welcome back in my class. Today I will take the topic electric dipole in uniform electric field, and with this I will also discuss uniform charge distribution. Students, now I am going to discuss dipole in uniform electric field. In this diagram, field is shown from left to right in both the diagrams, and since all the lines are parallel, which shows that the field is uniform, dipole with plus q and minus q and plus q both are shown here. Clear? Students, we know that when charge is placed in electric field, force acts on it, and that force is what? F is equal to QE. And we also know that the force on positive charge will be in the direction of field, while on negative charge it will be in opposite direction of the field. Positive charge here and negative charge here. Any doubt to anyone? No? Right. Okay. Here the dipole are placed in two conditions, like this and like this. Dipole are parallel to the field. In both the condition, dipole will remain in equilibrium. Clear? What will be the net force? The force acting on this charge is plus QE, and here it is minus Q, and net force will be 0. Similarly, minus Q is acting this direction, plus QE is acting in this direction, and net force is 0. And in both the condition, net force is 0, and both the dipoles are in equilibrium, but two conditions are there. One is the stable equilibrium and other one is the unstable equilibrium. Since these two forces are in opposite direction, when this dipole rotates by a very small angle, then these two forces will bring in equilibrium, and that's why it is in stable equilibrium. This dipole is here. In this condition, this negative force is acting. Negative force means minus QE is acting in this direction and plus QE is acting in this direction, like this. And if this rotates, this direction's force will try to rotate it and it will come in this position. Clear? Here this force towards the left and this force towards the right will rotate the dipole, and again then it will come in this condition, and that is why this is unstable equilibrium. Clear? Students, in these two figures, dipoles are parallel to the field. Now question arises that if we keep the dipole in the field making some angle with the field as shown here in this figure, yes, what will happen? From the figure it is clear that on plus q charge force will act in this direction, and minus q it will act in opposite direction of the field. So now topic we are going to discuss here is torque on a dipole in uniform electric field. Starting, dipole AB is placed in uniform electric field making angle theta from the field. The dipole length is 2a. The forces plus QE acting in the direction of field and minus QE acting in opposite direction of the field. Students, this diagram shows that plus QE and minus QE, which are parallel and in opposite direction, will form a couple which exerts a torque. And what is the torque? You know, torque is the product of force and perpendicular distance between two forces, and therefore tau is equal to, what was the force? QE. Torque was the force was QE. देखो, F is equal to QE, or this QE. Minus indicates only direction. So force is QE and perpendicular distance is what? One force this and one force this. QE minus QE, and this distance is the perpendicular distance between two forces. Yani BC. If we take triangle ABC, then BC is the perpendicular distance. And how you will find this distance? In this triangle, this is the theta, then sine theta is equal to perpendicular upon hypotenuse. We will see it. Therefore, torque is equal to QE into BC, and in triangle ABC, sine theta is equal to BC upon AB. Sine theta is equal to BC upon AB. BC upon AB. And on putting the value, we will get BC is equal to 2A sine theta. Clear? Now we put the value of BC in equation number 1. Tau is equal to QE into 2A sine theta. On arranging 2QAE sine theta, and 2QA is P, and therefore tau is equal to PE sine theta. Is that clear? Yes. Tau is equal to PE sine theta, and tau is what? Torque, moment of force, and it is the vector quantity. And if we know that the vector product of two vectors is the product of their magnitudes and sine of angle between them, and therefore we can write it in the vector form as torque vector tau is equal to P cross E, vector P cross vector E, right? And what will be the direction of the torque? As shown here in the direction, E is in this direction, dipole moment is here, and therefore torque will be perpendicular to both P and E according to rule of the cross product. You can see here in this direction, electric field is here in this direction, torque is in this direction, and therefore dipole moment is here in this direction, and electric field is here, and therefore torque will be perpendicular to these two, right? It is shown here. Clear? Now from equation 2, you can put the condition. If dipole is placed perpendicular means, you see here, this was making angle, this was parallel, and if we put like this, then angle will be what? 90 degree. So if theta is 90 degree, then tau is equal to PE sine 90, and therefore torque is equal to P into E. Sine 90 is 1. And in this condition, when dipole is placed perpendicular to the electric field, the torque acting on it will be maximum. One important condition, if electric field is unit and dipole is perpendicular, that is theta is 90 degree, then tau is equal to only P. Yes, E is the one, right? And therefore on the basis of tau is equal to P, we can define dipole moment, and it is dipole moment of a dipole is equal to the torque acting on it when it is placed in unit electric field perpendicularly, right? Students, we got the information about the torque, that is PE sine theta. And now there is one question, that an electric dipole of charges plus minus 1 by 3 10 to the power minus 7 coulomb separated by distance 2 centimeter, it is placed in field of 3 into 10 to the power 7 Newton per coulomb. Find maximum torque. Maximum torque means theta is equal to 90 degree, and therefore what will be the formula? Tau maximum is equal to PE only. If you write general formula, tau is equal to PE sine theta, Q given here 1 by 3 10 to the power minus 7, 2A separation 2 centimeter, right? So Q is equal to this, 2A is equal to 2 centimeter, yani A is equal to 1 into 10 to the power minus 2 meter, and electric field is given 3 into 10 to the power 7 Newton per coulomb, and for maximum torque theta is equal to 90 degree. So putting this value in this equation, tau is equal to P sine theta, P is not given here, so therefore we will use 2QA. P is equal to 2QA into E sine theta. We will get tau maximum is equal to 0.02 Newton meter, and you can calculate it. Students, now I am going to explain another topic of the same chapter, that is continuous charge distribution. What is it? One charge is uniformly distributed over the conductor in a space, then this is continuous charge distribution system. That is uniform distribution of the charge over a conductor. Clear? And there are three types of continuous charge distribution as given here. One is the linear charge distribution, surface charge distribution, and volume charge distribution. I will take the first topic, linear charge distribution. From the topic linear charge distribution, it is clear that when charge is distributed along a one-dimensional curve or a line in the space, then this will be linear charge distribution. Clear? Charge distributed along a one-dimension curve or line. Right? Now the thing is that what is linear charge density? Yes? Related with the same topic, linear charge density. This is the important point. Linear charge density at any point on this line is the charge per unit length of the line at that point. This is your linear curve. This is small distance dl, small length dl, and charge at this is dq. In this condition, linear charge density, which is denoted by lambda, is lambda is equal to dq by dl. Any doubt? Lambda, that is the linear charge density, is equal to dq by dl. The unit for q is coulomb, for length is meter, and the for unit of linear charge density is coulomb meter minus 1. Clear? Okay, class. Let us suppose this charge is uniformly distributed over a ring of radius capital R. Students, in linear charge density, if charge is distributed over a circle of radius capital R, in that condition, what will be the linear charge density? It will be lambda, na? And what will be its value? Q upon L. Q upon L. And for this ring of radius R, what will be the length of this ring? That will be equal to the circumference, that is 2 pi R. And therefore, linear charge density lambda is equal to Q upon 2 pi R. Clear? No doubt? Right. Next topic is surface charge distribution. Surface charge distribution. If the charge is uniformly distributed over a surface, this will be surface charge distribution. Right? And what will be the surface charge density? Which is the important point. The surface charge density at any point on the surface is charge distributed per unit area. This is surface charge distribution, na? And therefore surface charge density will be the charge distributed per unit area at that point, and it is denoted by sigma, and therefore sigma is equal to dq upon dy. This is the diagram which is showing any surface. This is area dA on which the charge is dq, and therefore sigma is equal to dq upon dA. Unit of surface charge density sigma will be what? Coulomb per meter square, that is coulomb meter minus 2. Right? If this charge is distributed over the surface of a sphere of radius capital R, since this is a sphere, its surface area will be 4 pi R square. Yes? 4 pi R square, and therefore surface charge density will be sigma is equal to Q upon 4 pi R square. This is your surface charge density. And on the same pattern, the last topic of this lecture is volume charge density. If the charge is uniformly distributed in entire volume, this will be volume charge distribution. And volume charge density at any point in the volume is charge contained per unit volume. Charge contained per unit volume at that point, and it is denoted by rho. This is three-dimensional figure. Charge is uniformly distributed. This is a small volume, yeah, dV. This is small volume, and charge is here dq, and therefore volume charge density rho is equal to dq upon dv. What will be its unit? Coulomb per meter cube, yani coulomb meter minus 3. Clear? And if the same volume charge density is discussed for a sphere of radius capital R, like this, means charge is distributed in its entire volume, then the volume charge density will be q upon 4 by 3 pi r cube. Pi r cube because of charge is distributed in complete volume of the sphere. Right? So now this is over. Thank you.